Konnichiwa friends, my name is Asmas Masi and welcome to part 3 of the music audio multiclass classification bootcamp. Okay, this is the part 3 of the bootcamp, and in this video we are going to revise the neural network, learn about missing basic CNN, also define matrix optimizer, loss function, and make a basic training loop with our CNN. And in our very next video we are going to learn about the CNN model more deeply, do some pre-processing, fine-tuning, and getting the better score here. Okay, so this video is all about mastering the basics of the CNN here. So starting with our optimizer, the loss function, and the matrix here. Okay, so we will first understand what will be taking our optimizer, loss function, and matrix for our bootcamp. Okay, so loss functions, it is in multi-class classification. We will be using cross entropy loss, okay, as our loss function, and it is the standard for our multi-class classification problem. Okay, so we use our cross entropy loss. Okay, it converts losses into probabilities and it penalizes the model heavily when it is confidently wrong here. Okay, so here the model penalizes based on whether the classification was wrong confidently or unconfidently. Okay, and it will reward confidently correct prediction. Okay, so you will get here output as something like this for the 10 classes here. Here each probability refers to probability for each class here. Okay, so 2.3 probability for our blues class, country class, hip hop, etc. till the very last 10 class. Okay, so first one is blues, second is country, then third is hip hop, and so on, etc. So here we are getting the losses probability for each class level here, and the final prediction will be based on the highest prediction here. Okay, here it will penalize the model if it was confidently wrong or reward if it was confidently correct. Okay, so after this loss function we will then go to our optimizer. Okay, so we will be using Adam as our optimizer. It is because the very fact that it converges faster and it is more stable across different problems. Okay, and it is more commonly used optimizer function. Okay, why not the others? So first is that SGD we could use, but it converges very slowly. Okay, and it also needs turning just like our momentum SGD. For ADA grade, learning rate shrinks too much over time, and for Adam W it is mainly used for model and transformers. Okay, we will use in our pre-trained model but not for our CNN. Okay, so we will be using Adam only. Also, one thing you must take care is that since we are using cross entropy loss and there are 10 classes here, our model must end with our NN dot linear only. Okay, so okay, because our BC law treat each class independently. Okay, and needs one logic per class. So we will be having, so whatever the model will be making, it will be ending with NN dot linear x comma 10. Okay, now for our next part is our matrix here. Okay, so we will be using F1 score as our matrix. Okay, why? Because it balances our precision and recall. Okay, it is useful when classes are imbalanced and false positives and false negatives both matter here. Okay, so since our competition will also be using our F1 score, we will be using F1 score only. Okay, the formula is 2 into precision into recall divided by precision plus recall. In short, it is the harmonic mean between the two which penalize large difference between numbers and become low if any one is low. Okay, so for example, if accuracy is less but precision is high, F1 score will also be low, and even if accuracy is high and precision is low, F1 score will also be low here. Okay, only and only when the accuracy and precision is high, F1 score will be highest here. Okay, this is because they are harmonic mean and they should increase together for F1 score to increase. This is an harmonic mean. Now why we are not using accuracy? It is because it can be misleading when classes are imbalanced. Okay, and now why precision? Because precision ignores false negatives and we want to consider false negatives too. Okay, now we have here how a deep learning model will look. Okay, so first thing is that we have our pre-processing part which we done in first 2 videos here. Okay, loading the data set and loading the audio file, then we make a model, then we define the model loss and optimizer, then is there a training loop, and finally there is testing phase. For CNN, the model must start with a convoluted neural network and ends with a linear layer, and it is to be defined inside the model class. inside the model class. So here we'll be making our model class for our CNN here. So we start by importing torch and importing torch.neural network as NN here. Okay, so here we'll be creating a new class here which will be our neural network class, and it will be taking our nn.module here. Okay, this model will tell the torch that it's an artificial neural network class. Okay, so we will write nn.module, then our def init, and we'll call the super class here. Then here basically we will be initializing all neural network and activation functions here. Okay, so inside our init class is the place where basically we define our neural network. So every neural layer or activation your function need should be defined here, and in our def forward it is basically for connecting your neural network and activation function together. Okay, so here it will be taking the x, and here by each x passes it will be connecting with one to the other. Okay, and here we will return x, which will be the connection of the whole neural network class here. Okay, directly here the x will go from top to bottom connecting the artificial neural and the activation function. Okay, so we have like 5 activation function where we'll generally be using nn.ReLU here. Okay, it is the one of the most common activation function as it ignores the negative values here and is widely used. Okay, for our basic CNN we'll be using our nn.ReLU here. Okay, activation function basically gives us non-linearity, and it is the one that makes our deep learning model deep. So without activation function our deep learning is not deep at all. Okay, so we'll be using our nn.ReLU here. Okay, now we are coming to the most common neural network that we'll be using in our CNN part here. Okay, so first thing is that let us make the forward function 2 here by it will be taking the self.x here, then it will be returning the first linear layer. Okay, now what is this convolutional layer? Okay, our question. So basically convolution layer is basically called the eye of the neural network, because this is the basically layer which basically see the image files in any computer vision project. Okay, it basically extract features like edges, texture, shapes and objects. Okay, and it uses actually filters that slide across the image to basically generate and see the final image. So basically you will see here that there is an image which basically have the grayscale here. Okay, and then 3x3 matrix is passing through each one of the image and it's extracting some features here. Okay, and this is basically what an CNN do to see the image by passing a kernel throughout the whole image here. Okay, and generating a convol feature which will then be learned by our deep learning neural network. Okay, so here we could pass the image through our first convoluted layer, then we could do max pooling or other convoluted layer, then we'll passing through our artificial neural network to understand the feature of the image and get spatial information. Okay, so this is the neural network which will basically see our spectrogram audio images. Okay, so here one thing you must understand that we are passing an kernel here. Okay, which will takes an input tensor and the convolution will slide a kernel across it and it will produce a feature map here. Okay, so we defined our Conv2D with first our feature map, then our out feature, and then our kernel size here. Okay, with our n. So x, y and n is the only thing required. So what are these? Okay, first thing is that kernel size define the matrix shape that will be passing through our image. Okay, so here the kernel size is the size of the sliding orange image that is scanning the image here. Okay, here it is scanning per 3x3 matrix here because the kernel size is 3 here. Okay, so if it is 3 then it will be passing 3x3 matrix. If the kernel size is 4 it will be passing through 4x4 matrix. Okay, now talking about the in feature and the out feature here. Okay, so what is the in channel here, and how basically we determine what will be the in channel here. Okay, for out channel it is very easy. For in channel you must understand the important concept here. Okay, so our convolutional neural network performs convolution over two spatial dimensions. Okay, for our Conv2D it will see the two dimension image here. Okay, so we have our x and y here for our image or the audio files here. Okay, it will have two dimension, or we can say x and y here. Okay, so the Conv2D basically takes batch size, channels, height and weight as 4-dimensional tensor here. Okay, so for the images, if you are talking about, or the audio files, if it is an image, it will be taking the batch, the channel, which could be 3 if it is RGB image, it could be 2 if it is in grayscale, if it is black and white it could take 1. Okay, then we have height and width of the image here, which basically determines the length and breadth of the image files. For our audio files specifically, it will learn this spectrogram, so it will be frequency into time, so it will be taking batch, then the one as in channel, which is an equivalent of black and white, then n dot males and the time steps. So here the n males is defined when we are making the male spectrogram only. Okay, and here only we pass the n males here, which will be basically equal to height of the image file, and it is basically saying that we are having the frequency band here. So for our convolutional neural network we must return this male here, it will be written as n males and timestamp. Okay, so whatever we were doing here will be not be returning our audio file, instead will be returning our male band. So here we'll be using librosa.feature the male spectrogram. Here we'll be passing the audio, the n males here as 128, and then our y. Okay, so we will be then using our librosa dot power to decibel to normalize it, and then we'll be returning this as toss.tensor and the label here. Okay, so with this we return the whole correct n males and time as an tensor here. Okay, now one thing you must notice is that we are getting 128 by time steps. Okay, but our convolutional network need as four tensor object. So basically what we will do is that we will do male dot unsqueeze here. Okay, so here in our returning tensor we will do the unsqueeze here in our 0th position to add an extra layer at the start here. Okay, and we will be returning this only, and here we make a new data set here. Here basically the unsqueeze basically add an extra dimension at the 0th position. Okay, at the very first part. So we are finally getting the final 3 tensor here. Okay, so if it is xy unsqueeze, will basically add an 1 comma x comma y. Okay, it will add an extra layer. To go back we will squeeze it. Okay, so when we will be initializing the data set here and we will be printing the first value here, you will see that it's an tensor object here with an 3-dimensional here. Okay, and it is the tensor which our convolutional neural network will lead, and by using our data loader we will be adding an extra batch size here. Okay, so we will be loading our data loader here, and here the batch size will be the batch size for our convolutional neural network part, and here our desirable size for our Conv2D will be done here. Okay, with our data loader, the unsqueeze and etc. Okay, so now we could pass the data loader inside our convoluted part here. Okay, so here the convoluted input takes our 4 variable tensor, but here in our in channel we basically type the channel name here. Okay, so if it is an audio or it is in black and white image, we always pass it as 1 here. Okay, we'll be passing it 1. If it is in grayscale, we'll pass as 2. If it is in RGB, we will pass here 3. Okay, in our in channel. For our out channel it is flexible and it depends on your design choice. Okay, generally we stack them together. So basically in our out feature you could put any value depending on your next convoluted layer. Okay, so here we are making a new convoluted layer named C2, which will have Conv2D, and here it should be same input as the output here. Okay, and we could pass here our choice output here, and here we could also pass the kernel size as 2 here. Okay, same to same. So here you will see that here the out feature will be equal to in feature of the second year. Okay, because it should be connected. The entire deep learning model should be connected. Okay, so here out feature equals to in, and here also it is the same here. Okay, so here the out feature depends entirely on our choice, and here we could type the kernel size of here 2. Okay, and next layer which you could learn is the batch normalized layer, which basically prevents exploding vanishing gradients. Okay, it doesn't do anything to the input tensor. Okay, it just normalize the layers here. Okay, so we could also add here BatchNorm2d, and here we will be passing out channel of the last convolutional neural network. Okay, it generally make training less sensitive to initialization and allow higher learning rate. Okay, it just normalize layer, it does nothing else. Okay, so if you are using batch channel height weight, it will be just normalizing it. Okay, so next we have our pruning layer, which basically reduce spatial size. Okay, it basically downsample, it reduce shape and width of the image. So here it affect the height and width of the incoming tensor here. Okay, so here it reduce shape of height and width. Okay, it is of two type. One is max pooling, with basically take the max of pooling layer, then which average pooling, which takes the average of the pooling layer. So for example, if we have an matrix here the max pooling will pass the first kernel until taking the highest value, which is 20. Then here we have 30. Then here we have 112 as the highest, so it will be sampling that, and here we have 37. Okay, this is what max pooling does, and it reduces the height and width here. Okay, so we could make here another layer name pooling, which will be doing nn dot max pooling here. Okay, so here if it is nn dot max pooling 2, it will be taking 2 strides per image here. Okay, so if you have 32, 64, 32, 32, it will be dividing the height and width by 2 here. Okay, for our incoming tensor here. Okay, so if the pooling is 2, it will divide it by 2. If it is 3, it will be dividing the height and width by 3. Okay, next we have our dropout layer. It is generally used during the training, which it prevents overfitting. Okay, it randomly makes the tensor value 0. Okay, so for example, if our input tensor is 2, 4, 6, 8, and if the dropout is 0.5%, so it will be basically making 0 to 50% of the value, and it will be completely random here. Okay, so by this we basically force our model to learn better features and doesn't rely on a single feature here. Okay, so by this the model will learn better, and it is only done during the training here, not during testing or our inference. And now the next layer is our flatten layer. Okay, we basically define it by toss.flatten. So here we forget our dropout layer, and now it's time for flatten layer. Okay, so it is defined by toss.flatten, and it is not an actual layer, but basically we use it for between our convolution and our artificial class. Okay, so if for example we have batch 64 14 14, then basically it multiplies the channel height and width here. Okay, so basically it gives us as only the batch size and the feature here. Okay, so the batch will be as same as that, only the channels height and width will be multiplied together to form a single value named feature. Okay, it is generally required as our nn.linear layer, which will be our next layer for our artificial neural network, basically needs in batch and features only. Okay, so basically we'll be using at the terminal of the convolution layer. Okay, And now it's time for our linear layer. Okay, so linear layer is the final decision layer, and it is a fully connected layer of our basic artificial neural network. Okay, so one thing important is that since we are using BC with BC loss here, our neural network should always ends with our self dot linear and dot linear. Here we will be putting x comma our 10, because we have 10 classes here for our prediction. Okay, so our linear layer should always end with our 10 value. Now for our next question is that how do we determine the n dot linear x feature here. Okay, so you must also keep in mind the torch dot flatten here. Okay, so here the n dot linear basically we get from the channels height and width multiplication of our incoming tensor here. So basically here 1244 basically get from the torch dot flatten layer only. Okay, so here we will be taking 64 into 14 into 14, which basically we got from the channel name which we done here. Okay, so here our x will be the value of 64 into 14 into 14 here. Okay, so here we will be putting it 1254. Okay, so now you may be asking that is instead of like manually counting here, is there not any easy or any secret way to do this? So yes, I would like to tell is that there is a secret to solve this problem. Okay, and that is that adapting pooling 2D. Okay, so instead of manually computing the final spatial size for our linear layer, we basically use our n dot adapted average pooling 2D here before our linear layer, adding the adapted average pooling layer. Okay, so this will basically force the incoming tensor to custom height and width. Okay, and the only thing you need to remember here is the channel here. Okay, so here it will force the height and width of the input tensor. So we have our batch size channels height and width, and by after forcing we will only need to remember the last channel name here, and the height and width will be forced to 1 here. Okay, so we need to only remember the last channel size here. Okay, which is 64, and we need to pass it here only the same 64 number here to finally get the final tensor here. Okay, so here then finally we will be joining each our neural network here by passing x throughout the whole layer here. Okay, so first we pass through our first C1 C2, then normalize, then our pooling layer, then our dropout layer, and finally the adaptive layer and the linear layer. Okay, so for the linear layer we could also stack them together. Only our the last feature 10 should be here included here. Okay, so n dot linear 100 by 10, and we could also include our ReLU function here between the linear layer. So the things we must make sure during our layer is that we must make sure we are using torch dot flatten x/1 to flatten the convoluted layer before the x is going to our artificial neural layer. Okay, so we basically joined the layer. Now it's time for initialization, the criteria and the loss function here. Okay, for initializing we directly put the class name here, and then for our optimizer we use our cross entropy loss as our criterion equals to n dot cross entropy loss here, and then for our optimizer we'll be using torch dot optim dot atom here, and then we pass the model parameters which we thus define and a small learning rate here. Okay, so with this we actually initialize our model loss and optimizer. Okay, first we initialize the model, then we define the criteria, and then if you want to use here optim only, we actually import torch dot optim as optim here. Okay, so now the optimizer part will be called by optim here, and we pass in small learning rate so we could train easily. Okay, So here basically we initialize our model, loss and optimizer, then it's time for training loop. Okay, so the training loop start with for epoch in range, and then local value by total loss, and inside the loop we run an loader which will basically get the images and our labels, and we pass to the model, and then we find the loss here. Okay, so we start with 4 epoch in range, 5 here which will be taking our loader. So we do 4 audio and label in loader, and then we, so here basically it will be doing batch wise, okay, training. So here basically the output will be getting from model, which will be taking the audio, and here will be calculating the loss by first passing the output and then the real label. Okay, so here we could also print the epoch, run, and we could run it. Okay, so you will see that it will take some minutes to run here. Okay, so here basically we first get the prediction from model, and then by criteria we are actually calculating the loss here. Okay, so for the full loop it will take very much hours to learn. Okay, so what we'll do here is that we'll be adding the break here for our each, and you will see that it basically prints the whole value here. Okay, so we now will be adding our optimizer the zero gradient, which basically clear all gradient, then we do the back propagation through our model, and then step here. So we do by optimizer dot zero gradient here, zero grad, and then we will do our back propagation for our deep learning model by doing loss dot backward, and then finally we will doing the optimizer dot step, will doing optimizer dot step to update the model parameters. Okay, so by this our whole loop will be ready here, and here we will be now printing the total loss here. Okay, after each epoch here, and we are also deleting the break here. So you will see that now it will take very much time to load here. Okay, to solve this problem, in our last video we learn about the device and also sending to device for our CUDA. Okay, so like we had already initialized the device here, so we'll be running our GPU P200 for our whole data set. Then here we'll be sending the model to device, then here the audio also to the device here. Okay, so we'll be doing audio to our CUDA, then our labels to our CUDA too. Okay, so if you will be running, you will see that here first we send our model to our CUDA, and then finally after running everything, you will see that we basically send CUDA, and here I wrongly write label here, and you will see that it will now take much less time than our whole part here. Okay, so when we'll be running this entirely, you will see here the final loop here. Okay, so let's wait here just a few minutes to run it. You will now see the final output here. Okay, so it will take just a few minutes to run. Okay, so until that time, so let's summarize everything we had done so far. Okay, so starting with here, first we first making dataset here which will take all files, and then we will be loading it, and then inside our length we'll be returning the length here, then we'll be catching the audio files here. This is new, so you could copy this, and also you could find this in my GitHub code here. Then we'll be getting the max time for our audio here, and then we'll be basically deleting the audio files which are more than the length, and then we convert it to MEL spectrogram here, then we normalize, and then we return the normalized tensor with our unsqueeze here. Okay, then we make the dataset class, and then we make a small CNN model, and also here we pass the ReLU function after each Conv2D here, and here also we make sure for our channel here. Okay, for our batch normalization here it should be same with our output layer. Here we do max pooling, then our dropout layer, then we have our max pooling layer, and then we have our adaptive pooling layer, and here between our convolution and our artificial we add our torch.flatten x.1. so don't forget that, as it is very much important here. After our adaptive average pooling 2D, then we import torch.optim, and then we initialize my model and send it to our CUDA. Then here I define the loss criteria and finally the optimizer, and then here I make the final training loop, and here you will see that the first epoch is successful and the loss we get here is 73.6519. okay, so by this the whole setup will be running from epoch 1 to 10 or 100 here. okay, so by this here we will be training the whole part here. okay, this is basically how we'll be training. So that's all for today. We learn basically how to make a basic CNN and also understand some neural layer, okay, and how to do basic training. okay, in our next video we will learn how to make the base CNN, do some pre-processing, fine-tuning the result and getting a better score. okay, so this video is all about mastering the basics. okay, that's all for today. Thank you and bye bye.